Those who have joined, kindly, mm, comment in that comment section so that I can understand. My voice is audible. Yes, I can see Bani, Oishi, Shurjani, Konkonika. Okay. So our topic is work, power, energy, and we'll see important numericals based on work and energy basically, and we'll see something about like potential energy, gravitational potential energy, all those topics. Correct? Oishi, we have done up to kinetic energy, na? So we'll wait for some 2-3 minutes for others to join. Yes, we have done the numericals also. Okay. Okay, so we'll start with potential energy. We'll start with potential energy. Okay. Okay. So basically, what do you mean by potential energy? Potential energy. So it is the energy possessed by any object or substance by virtue of its position, or in other words we can say it is the energy stored, it is the energy stored inside a body if you want to change the position or the configuration of that object. Okay, so it can be, so actually it is a common definition, that is energy stored within the object by virtue of its position, by virtue of its position. Okay, or acha, by virtue of its position in a field of force, that means the force should be there, there must be a field of force like gravitational force. Okay, in a field of force, obviously if there is no force, then there is no meaning of this type of energy. Okay, because force is connected to the work done and work done is actually connected to the energy. Okay, so in a field of force or by its configuration. So therefore it is clearly uh, you know it is clearly understood that it is not only about the position. You just think about the springs. What happened for the springs? You have a spring, so especially the helical spring, because springs are of many types, helical spring, slip spring. Okay, so this is a common type of helical spring. If you apply force, okay, in this direction, बानी वो दो तो मैं बोला था ना संडे को 11 एम, वो होगा, वो टॉपिक होगा. ओके, अच्छा, see if we apply force in this direction, what will happen? This spring gets stretched in this direction. Okay, therefore what you can say, there will be the change in the length. Suppose the initial length is L and it gets stretched, so the length get changed. And suppose we are considering this change, or if the initial is L and this is actually your L plus delta L, so therefore the change is delta L. Therefore this delta L is also the reason to that means to store potential energy inside the spring. How you can basically realize it? See, once you stretch it, again it has a tendency, because due to the elastic property of the spring, it has a tendency to come back. So who will provide its energy to come back? It's the potential energy inside the spring. Once you stretch it, already due to the change of that length of that spring, already the potential energy is possessed inside the spring, and therefore when you just remove the external force, again it regain its original shape. So to regain its original shape, it must have some energy to come back, so that energy is provided by the potential energy. Okay, now, so this is a kind of potential energy. It is not like the potential energy we generally understand, like mgh. Mgh is a kind of potential energy that is under the influence of the gravitational acceleration. Okay, now see, there is certain terms that we understand about this potential energy. So potential energy is also known as mutual energy. Potential energy is also known as mutual energy. Potential energy is also known as mutual energy. Okay, that means why it is actually named so. So it is the measure, it is measured by the amount of work that a body or a system uh, can do, uh, just it's changing the position or the configuration. So why it is a mutual type? Because see, in case of spring, what happened in this case, you stretch a spring, you stretch a helical spring. Now the length gets changed, and when you basically withdraw the external force, it gets its original position. So therefore you can say the external force that you are applying to it to change the configuration of the spring, and you cause a delta L deflection or change in length. Again mutually the energy is getting transferred into the spring to get it back in original position. So whatever the force you are applying on it and changing the length, that energy stored inside it, so that first you have done work done, because something you are stretching, you should do work, and that work is converted, or we can see, we can tell it is stored in the form of potential energy inside the spring, which helps it to come back its original position. Any kind of elastic thing, we can see this type of condition. So here it is not the change of position but the configuration. So this type of potential energy is known as elastic potential energy. Elastic potential energy. Elastic potential energy. Okay, clear? Okay, now we'll see some other topics related to this thing, like uh, here first thing that comes in our mind, that is gravitational potential energy, because elastic potential energy is something that comes later. First we should understand what is mgh, and we most of us, we know about mgh, that is the potential energy, and it is nothing but as it is said in our lower classes, like if m mass object is basically displaced at a height h, or you can bring a, you are taking a m mass to a height of h against the gravitational acceleration or under the influence of the gravitational field. So therefore the work done is actually the mgh, and that is actually the potential energy stored inside the object. So that is the basic concept of gravitational potential energy. So what we can say in this case, in a pictorial representation, suppose you have an object, let's suppose this is a rectangular box. Okay, it is there, box A, and suppose this position I can consider it is x0 because it is the ground. Okay, now here the only force acting on it when it is lying on the ground is mg, if we consider m is the mass and g is the gravitational acceleration. Now we are basically lifting it up at a height x is equal to h. Now this is the same object I took over here, and therefore you can say, so when you replace it, or when you basically place it over here, lift it over here. So therefore the work done is actually force into displacement, and as you can see you are lifting it up. Okay, you are lifting it up, and actually if you consider you are forcing it to go up or you are lifting it up, therefore the force you have applied and the displacement all lies in the same direction. So therefore the angle which it makes with the applied force is 0. So cos 0 is 1, so you can say W is equal to Fs. Now here comes another question you might ask me, sir, we know these type of things are actually negative work. So yes, it is negative work if you consider the force to be the weight. If you consider the force is the weight, the force is the weight. So you are basically doing work against the weight. Weight is a force. Weight is a force, or you can say gravitational attraction also you can say. So this is another form of gravitational attraction only. So that is there, that is downward, and you are doing work against it. So it is, in that sense, it is negative work. But if you consider that you are lifting something up, so therefore that your applied force and the displacement all lie in the same direction, that is vertically upward. In that case, the theta is 0, not 180 degree. Clear? So it depends on the what force you are basically considering. Okay, so therefore what we can say in this normal case, if W is equal to Fs, now here if you consider the force you are applying, that is exactly equal to the mg, that means you are just able to lift it up, you are just able to basically nullify the effect of weight. So what we can say, this F is nothing but is equal to the mg, that weight of that object. Therefore I can say it is mg into s. Now s is here nothing but 0 to h, so you can say it is h. So therefore you get this relation mgh, W is equal to mgh. Okay, now here comes one question, and you can say this is equal to the potential energy. Potential energy you can write Pe also, or you can write U also. Okay, now here comes another question. What will happen potential energy or gravitational potential energy on the surface of the earth? Just give me the answer. What will be the gravitational potential energy on the surface of the earth? Give me the answer. In this chat box, you give me the answer. Yes, yes, because the height in that case h becomes 0. Okay, so it will be 0 in that case. So acha, it depends on the situation. Like, then what will happen, what will happen if this you consider the potential energy in case of uh, uh, moon, what will happen to that? Suppose I am considering potential energy to be 120 joule for a certain height, for 10-meter height from Earth's surface. Now, what will be that potential energy at for the same height on the surface of the moon? Can you tell me? Can you tell me? Yasika, are you there? So I was asking that if the gravitational potential energy at a height of 10 meter from the Earth's surface is 120 joule, what will be the gravitational potential energy for the same object for the same height in case of moon? Ognivo, are you there? I have repeated the question. Why you are thinking so much of it? It is a a very simple case of gravitational acceleration only, because you can see u is basically proportional to g. So in case of moon, this g will, we know it will be 1/6, correct? So therefore this potential energy in case of moon will be 1/6 of it, 120 into 1/6. So it will be 20 joule in that case. Why 190.6, 195.6? Why? How you get like this? See, basic concept is that to lift an object on the surface of the earth for 10 meter, if it cost 120 joule of energy or work done, definitely in case of moon it will cost 1/6 of it. It will cost more less, na, lesser value. Why? Because that acceleration, gravitational acceleration is much more, 1/6 of it. Okay, you understand? Hello. Yes, if you consider, yes, if you consider that thing in that way, like, yes, 19.56. Okay. Now we are going to the another topic, that is conservative and non-conservative forces. But before that, uh, I'm just asking, have Ognivas joined or not? Ognivo and Yasika, I don't know why they have not joined. बाकी कौन कौन ज्वाइन किए, just just reply me, except of Oishi, Bani, Kankonika, Shurjani and Rupam. Except these people, just reply in the chat box. Shutopa is there, okay. Shutopa, we are discussing potential energy, okay. Anyone else? Okay. Okay. Now, what is conservative and non-conservative force? Okay. Conservative and non-conservative, conservative and non-conservative forces. See, what is the parameter, that is, what is the deciding factor to say whether this force is conservative or not? So, a conservative force is that type of force if the work done by the force in displacing a particle uh, is actually independent uh, of the path followed by the particle and dependent only the end point. Suppose you were basically applying force to displace a particle from one point to another point. Okay, this particle A, you are displacing from this point, suppose this is P point to Q point. Okay, now you are applying force on it. Now which force will be conservative in this case? So suppose there are n number of possible ways to displace the particle, this P of A object from P to Q. You can displace in this way, 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 and so on. So therefore, a conservative force is the force which will not depends on the path that the particle follow to displace from P to Q. It is independent of the path what basically the particle follow. So it is independent of that path. Okay. So that type of force is known as conservative force. So if you see, normally if I am showing here A to, suppose 2 points I am showing here, A to B. Okay. Suppose from point A to B, a particle moves from A to B. Okay. So from A to B it is moving in this way. It can move in this way, or it can follow this path also, or maybe a straight line also, or maybe a straight line also. Okay. Then the work done on the particle is same along the two paths. If I consider this is path 1, path 2, so work done to displace a particle from A to B, I am representing WAB along 1, path 1 is equal to WAB along 2. So this is the nature of the conservative force. This is the nature of the conservative force. Do you understand? Okay. So what is conservative force? When you applied a force, you want to displace a particle from simply one point to another point, you need to displace a particle. But the work done by the force doesn't depend on which path that particle follows. That means n number of path is there. So n number of work done will be there, but all of them are same. Clear? Now you see, if we consider this case, we should consider another case also. What is that another case? That case is, if from point A to B, if you want to displace a particle again from A to B, but what happens here, it is a roundabout trip, like A to B is going path 1 and it is coming back from B to A again, but it is first going and then coming back. Huh? So it is a round trip. So what happened in this case? In this case, for a conservative force, this will be WAB along path 1 is equal to minus WBA along path 2. Clear or not? Okay. So therefore, this is how you can basically classify the negative thing in this way. So when we consider it is A to B, it is positive, but the returning path, it is negative. So they are basically equal in magnitude but opposite in direction. Clear? Now, so therefore what you can say, if you consider, see, now here is an interesting point is there, if you consider this thing a closed path, like from A to B then B to A, this is a closed path. Do you know what is a closed path? That path which starts from a point and then it ends on that point only. So it starts with A and it ends on A only. So then it is a closed path. So therefore, what conclusion you are arriving from this concept, that is work done AB along 1, and now you bring this minus in this side, plus work done BA along 2 is equal to 0. So work done in this closed path ABBA, this is a closed path ABA, you can say it is ABA. Don't write ABBA, you can write it is ABA, because closed path is equal to 0. So this is a concept, important concept. If you have closed path, they have asked you about the work done, that should be 0. Okay. Clear? Clear na? Now we will be considering a different type of topic, or rather I can say a question that can be asked from that topic, that is potential energy in relation to conservative force. So give the heading as potential energy in relation to conservative force. Potential energy in relation to conservative force. That means the amount of energy possessed inside the body, how it is considered to be relate with conservative type of force. Suppose you are considering a conservative force Fx. When I say Fx, as you know, this thing is actually denotes this F force depends on this x. So force is a function of x. X is the displacement. Okay, x is the displacement. So as the displacement changes, the force gets changed. Okay. So if we consider Fx to be a conservative force, conservative force. See, conservative force. Okay, and we are considering it to be a one directional. That is why I have given x. Rather, I will give x, y, z, all the three dimensions. Okay, and it does work W. It does work W. That means this force applied on an object and the work done is actually W. And the potential change of potential energy is delta U. We are considering it to be delta U. And delta U, we know this potential energy is equal to the negative work done by a conservative force. It is always true. When you consider a conservative force, the change in potential energy is the minus W, negative work done. You just take a note of it. Okay. Okay. So delta U means change in potential energy, that is equal to negative work done. Negative work done. Okay. Now, what happened in this case? We know one concept, that is W, from the concept of work done by a variable force, from the concept of uh, work done by a variable force. Okay, from that concept we know W is equal to, W means, so for the work done by a variable force we know dW is equal to Fx dx, and therefore if you integrate both the side and if you consider the distance to be x1 to or x initial to x final, so we can write it simply this W, because dW if you integrating it is W is equal to this integration x initial to x final position, so f x dx, that you can say. Okay, but from here, from the work done by the conservative force, we know delta U is equal to minus of this work done. So minus of this x initial to x final Fx dx. Okay. Now we need to differentiate this equation. We need to differentiate this equation. How do you differentiate it? Simply, while you will be differentiating it now, this delta you just make it du, and this dx is here, so bring it below this du, so it will be dx, du by dx, and that is equal to minus f of x, minus f of x. Okay. Now, therefore, what you can say, this f of x, that is the conservative force, is equal to minus of, because if you multiply both the side with negative thing, so it will be minus du by dx. Now here, when I say this du, this thing na, this capital U, uppercase, okay, you should write a x, that is this, U is also function of x. U means potential energy, definitely it should be a function of x position, we know it. Okay, so what you can consider from this, or what is the conclusion that you can draw from this concept, like potential energy can be defined as a function of position whose negative gradient gives the force. Potential energy U may be defined as a function of position whose negative gradient, see this is minus du by dx, so it is a negative gradient, whose negative gradient, gradient, this du by dx, this concept, whose negative gradient gives the force, whose negative gradient gives the force. Okay, or you may say similarly, like in the reverse way, vice versa, you can say conservative force can also be defined as, because see, Fx, this is a conservative force. Conservative force can also be defined as the negative gradient of the potential energy, isn't it? So conservative force can also be defined as the negative gradient of potential energy. Okay, this is how you can conclude it. Now, gravitational force. Gravitational force as a conservative force. If this type of things they have asked you, gravitational force as a conservative force, what you can write in that case? See, you should keep this type of derivational construction, same thing, only in place of x you just write h. And you can basically do one thing for the gravitational force, for gravitational force, for gravitational force, what you can do, you consider the potential energy UH, that is equal to mgh, because this potential energy U is a function of h, it varies with the h, because m and g cannot be varied. Okay, so this is one variable here. Even any kind of energy, let it be potential energy, let it be kinetic energy, you'll be having that one variable. Mass cannot be varied. Okay, in case of kinetic energy, half mv square, m cannot be varied, so you should rely upon the v square, and here mg both cannot be varied, you will again rely upon the displacement, that is h. Okay, now in this case, if you take the negative gradient of this fellow, that u function of h, if you take that negative gradient, that is minus du h by dh, then that will give you minus ddh of this thing, this mgh. Simply we are differentiating both the side with respect to dh. Okay, so if you differentiate, so here what you will be getting, you will be getting minus duh, the same thing that you will be getting over here, and here you will be getting, because mg that cannot be changed, and h, that if you differentiate dh by dh is nothing but 1, but it is negative in that case also. Okay, so this minus mg. Okay, now can anybody describe why I am getting it minus mg? I need that explanation from you. You can write in a very small explanation. I need one line or maybe two word, 3 word. You can explain it. Why it is negative? Huh? Why it is negative? Why this is minus mg? A very fundamental question. Why it is minus mg? I need it quickly. Just think it and just answer it. Just type it quickly. It's a rapid fire. Why it's negative? Acting downward. See, acting downward, the force is acting downward. Nah, the thing is minus mg. Force is acting down. Mg is always acting downward, but we are not supposed to say it is minus mg. The thing is that, yes, gravity acts downward, but here this conservative force, yes, which is basically used to uplift an object from a height, is against that mg. Therefore the force which helps it to go up is negative that of this weight. So the direction is upward there for the force you are applying to lift an object, which is against the mg. Therefore, this minus mg. Mg is downward, it is anyway, it is downward. But when you are lifting something, therefore you are basically supplying the potential energy to it. And it is against that gravity. So therefore against the weight. So it is negative. Clear? Yes. Yes. Okay. Now moving to the next concept, that principle of conservation of mechanical energy. You know, all these things are comes under mechanical energy. We are actually here to consider only the mechanical energy. Let it be kinetic energy, let it be potential energy, but all the things are actually in the form of mechanical energy. We have n number of forms of energy. We have sound energy, light energy, that is we have electromagnetic energies, we have nuclear energies. All those segments have different classification. Only we are considering the mechanical energy. Why so? This thing is quite relatable with the daily life, that is the laws of motion, displacement, acceleration, all those things are correlated. That is why we are only focusing, even the curriculum also focusing on the mechanical energy part. And most of the applied area of this portion is actually based on the mechanical energy. Okay, now the principle of conservation of mechanical energy. Principle of conservation of mechanical energy. See, to prove this thing, first we will be taking a general condition. We'll be taking a general condition. The principle basically states that if the conservative force are doing work on a body, so you need to consider, you have a clause like this. The statement should consider one important term, that is conservative force on action. If you are not writing it, the work done is not by a conservative force, if you are not mentioning it properly, then you might have lost your marks, because this is very much important. The principle should include if only the conservative forces are doing work, conservative forces are doing work on a body or object, then the total mechanical energy being conserved. Then the total mechanical energy, total mechanical energy means what? Ke plus Pe, kinetic energy plus potential energy, remains constant. Okay, how to prove it? Suppose you have an object that undergoes a displacement of delta x. Object undergone displacement of delta x under the action of conservative force Fx. Okay, so delta x is the displacement by the object under the influence of a conservative force of Fx. So therefore the work energy theorem says change in kinetic energy is equal to the work done. change in kinetic energy is equal to the work done, Fx into delta x. So change in kinetic energy, and now as the force is conservative force, we know, therefore change in potential energy is equal to negative work done. We know it, just we have written that concept. So minus Fx delta x. So for change in Ke, for work energy theorem, change in Ke is equal to Fx delta x, the work done. And as per the conservative force concept, the change in potential energy is equal to the negative work done. Okay. Therefore, you can say delta Ke, that is change in kinetic energy, is equal to negative change of potential energy. Yes, that is quite true. You can see when the kinetic energy is getting increased, the potential energy is getting decreased. There must be, no point in possible for in Newtonian frame where you have maximum potential energy, maximum kinetic energy. If you have maximum potential energy, definitely the kinetic energy should be zero in that case, and vice versa. Correct? So therefore, delta Ke plus delta U is equal to 0. Or we can say, we can take delta, a common factor, so Ke plus U to be 0. So Ke plus U, delta of Ke plus U 0 means there will be no change of these two fellow when they are added to each other. So that they are added to each other means they constitute the total mechanical energy. So their change is 0. So they are actually the constant term. They are constant. Okay. So what we can say at the end, kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. This is what the statement said. Clear? Yes or no, batao? Are you with me? You understood the concept? You know about the concept, but here how you have to represent this in this way, because this concept is nothing new to you, correct? And very small, grades or classes you were learning this, but you need to represent in this way. Okay, from now onwards. Okay, now we are another concept is there, uh, for, and that is quite familiar concept for all of us: conservation of mechanical energy in a free falling object or body. So let us consider that topic, that topic, subtopic rather, I can say subtopic: conservation of mechanical energy in a freely falling body. So first we should consider some specific points. Let's suppose this is a ball, this is the point A, in between middle of the journey the point B, and end of the journey with point C. This is where it is going to touch the ground. Now, but the C point is not exactly the ground, it is almost before it touches the ground, that's all. That means the difference is quite less. That means there must not be that any h. H can be neglected in that case. Okay. Now, suppose the total height from A to C, I can consider to be h. and A to B, this distance is x, therefore B to C's distance is h minus x. Okay, now at point A, we know velocity at point A should be 0 at the topmost point, because we are considering it is freely falling, no velocity is supplied to that object, free fall condition. Okay, now kinetic energy, naturally, if it is velocity is 0 means kinetic energy at A will be 0, and potential energy in that case, and we can say it is U at A, is the highest value, so mgh, because it is h height. So the total mechanical energy, total mechanical energy is equal to, I can say it is EA, that means total energy at point A, that is Ka, kinetic energy at point A, plus UA, and which is equal to your mgh, because Ka is 0. Okay, now consider point B. Let us consider point B. What happened in this point B? Because the object is fall from point A, and definitely it will gain some velocity, okay, because it falls from 0 velocity, but at point B it should gain some velocity. So we can consider the time independent formula to get the velocity at B. That means V square is equal to U square plus 2G. But we can consider one thing, see here, because the velocity what it gains, it is in downward direction, isn't it? It is in downward direction. So we can say it is minus V square is equal to U square is 0 minus 2G x, because this G is negative now, that is why it is minus G. So anyway it is getting cancelled, so V square is equal to 2Gx. So we can say it is VB, correct? So VB, so I can keep in this way, because my formula is actually half mv square. So KB, kinetic energy at B, is half m into VB square. So it is half m into 2Gx. So you get mgx. Okay, so this is your kinetic energy. But what will be the potential energy? Because you should consider always potential energy the height from the ground. From the ground it is h minus x. So mg into h minus x. Now if you add both of them, total energy at B is equal to kb plus ub, and it is nothing but kb is mgx and ub is mg into h minus x. So you clearly it is mgx minus mgx plus mgh. mgx get cancelled, so again you are getting the same quantity that you got earlier in point A, and that is the point of proof. So we got at point B the same thing, total energy is mgh. Now point C. Now when we consider point C, because it is just about to touch the ground. So about to touch the ground means it has not touched the ground. If it touches the ground means it basically disperses the energy, dissipate the energy to the ground, and the energy get converted to sound, heat, all the possible forms. Okay, but C point is very vital. It is not exactly the ground, but it is almost the ground. Like the height from ground to the sea is negligible. Okay, so therefore for C we can use for calculating the velocity at C, that could be the maximum velocity before it hit the ground. So we can use the time independent formula, the same formula. Again, the negative velocity v square is equal to so this thing. Uh, but what happened in this case, you see, so finally we'll consider from the initial zero velocity, 0 minus 2g. So here it completed the total journey. Okay, minus minus get cancelled, so v square is equal to 2gh. Okay, now if this is vc square, now kinetic energy at c is equal to half m vc square, which is nothing but half m vc square is equal to 2gh. So 2 get cancelled, you are getting mgh, and potential energy, you know, mgh, h is 0, so 0. So this total energy E at C is equal to Kc plus Uc, and nothing but mgh, the Kc, the total Kc, and this 0. So it is mgh. So here you can prove how the energy being conserved in all the 3 points in this journey for a free falling object. Okay, clear? Clear or not? Bunny, which portion you are saying to repeat? Which one? Can you be very little bit specific? Which portion you are saying to repeat? Na, you're asking me something to repeat. Can you just be specific little bit? Which portion? Point A. Yes, I'm going to the point A. See, here because it is the maximum height, not only the maximum height, it is free falling. So initial velocity in that point is 0. So I am considering velocity of that object in that point is 0. So v 0. So kinetic energy is 0. Potential energy is maximum mgh. Yes. Therefore, energy, total energy is equal to Ka plus Ua. So mgh plus this K is 0. So that is the total energy. And so once it is proceed to the point B, therefore, what happened? We can use the time independent formula. This vb square, because at point B the velocity would be vb square minus, because it is going down, again that concept, vector concept, don't forget about it. Okay, once it is going down, negative velocity, negative direction due to the direction. But see, initial velocity was 0, and as it is coming down, not for the coming down, actually it is g is minus, negative, so minus 2gx, so negative negative get cancelled, so vb square is equal to 2gx. Now you get the kinetic energy half m vb square, just do it. But the potential energy in this case, because you need to take the height from the ground it is h minus x, so mg h minus x, and therefore it is actually the total energy in that way, mgx plus mgh minus x. So mgx mgx get cancelled, only you will be having mgh. And at the end of it, at point C, because the potential energy will be 0 due to the height is near 0, negligible, C at that point C, and that if you consider the velocity at C, it should be throughout the journey, you should consider total journey. Initially it was 0 minus 2gh, as it has covered the total distance. So vc square is equal to 2gh. So you will be having kc is equal to mgh. Therefore total energy at C is equal to mgh plus 0. So it is actually mgh. So this is the way you can describe it. Okay. Now here is a graph that is very much important uh, in relation with this type of variation of energy with height. Very much important graph. If I consider energy in y axis and height in x axis, so we know kinetic energy is actually maximum at 0 height. So this is your 0. So I'll start with kinetic energy. As the height increases, because x-axis represents the height, as the height increases, the kinetic energy is basically decreasing from from maximum to zero. Okay, because this is the maximum kinetic energy. So this is your kinetic energy line, kinetic energy line, because you see this is your zero. In x-axis you consider the height is in x-axis, so this is zero, and this is suppose the maximum height h. So at zero height, the kinetic energy line is actually having the maximum value. As the height increases, the kinetic energy drops to zero. At height h, it is zero. Opposite happened for potential energy. At zero, it is zero. As the height increases, it increases to maximum value. Okay, and therefore we can close this rectangle type of thing, and this up value is actually total energy TE, that is KE plus PE. So total energy, which is parallel line to the height axis or x axis, denotes that it is a constant quantity. If your y axis quantity is parallel to the x axis quantity, therefore what you can say, the y axis quantity doesn't change. So that denotes by this line. Okay, clear? All of you clear of this concept? Clear? Clear up to this? Clear or not clear? Jessica is there or not? Okay. Now let us consider some important numericals in this, which is basically related to this type of topics what we have discussed today. Okay. First numerical that is there. Let me write down that thing. Write down the statement of the numerical. A vehicle of mass 15 kg climbs up a hill 200-meter high. It then moves on a level road with with speed of 30 meter per second. 30 meter per second. Calculate the potential energy energy potential energy gained by it gained by it and its total mechanical energy, and its total mechanical energy while running on the top of the hill, while running on the top of the hill. Find it out. Basic type of question. Give me the answer. Give me the answer. First, what will be the potential energy? First, you calculate the potential energy. Then the total energy. Total means kinetic also needed plus potential in that case. Potential, all first you have to calculate potential, then you add with the kinetic, then that will be the total energy in that case. Potential energy is yes 2 na, yes correct. Yes, 15 into this G, if you consider 9.8 also, and height is 200. Yes, that answer is correct. Yes, Oishi. Mechanical energy is yes. Yes, correct. Absolutely correct. Because kinetic energy will be half mv square in this case. Correct. Just add both of them. That's all. Yes, correct. Correct only. Why you? Acha. Yes. What about others? What about others? Only Wishi and Bani have replied about it. Okay. Okay. Let us consider another problem. Little bit different type of problem. Okay. The problem statement is a girl a girl of mass 40 kg sits in a swing, in a swing formed by a rope of 6 meter length, 6 meter length. A person pulls the swing, pulls the swing, pulls the swing to a side so that the rope makes an angle 60 degree with the vertical, with the vertical, sorry, vertical CL. Yes. What is the gain in the potential energy of the girl? What is the gain in potential energy of the girl? Girl of mass 40 kg sits in a swing formed by a rope. Rope, what is the length of the rope? 6 meter. Person pulls the swing to a side so that the rope makes an angle, because you need to pull it na, so that it can swing it, correct? Okay, so that angle makes 60 degree with the vertical. And what is the gain in potential energy? When it will gain the potential energy? When some person pull it so that it makes 60 degree angle, isn't it? So you have to imagine it, you have to represent it in a pictorial diagram. See, pictorial representation is not mandatory for the problem, but for your understanding it is, you know, it is needed. Okay, see, those who are doing, you just don't see the answer what I am doing, just you just do by yourself, and I am also doing for others who are not understanding this concept. So if this is my vertical plane and this is my horizontal plane, and because the rope is basically pulled by some person, this is the position of this rope, so maybe the girl is sitting in this position, and this is the 60 degree, because someone is actually pulling it in this direction and holding it here. So mm, so the original position, because this is a position of a kind of extreme of a pendulum, the original position may be here. Okay, it will swing and it will come to this mean position like this. So what we can consider in this case, what we can consider in this case, we can name, yes, Rupam's answer is correct. Rupam gave me a answer which was correct actually. Yes. So what we can consider here, I can consider ABC, this triangle. I make a triangle ABC. Angle is 60 degree, and this is the right angle, and this is the swing. This AC is the swing. AC is the swing in this case. Okay. Now what you can consider, if this is the mean position, suppose this position is O, so OB is the mean position, so this height from O to B we can consider the H, because this height is what, when this swing is pulled, this height is covered by this girl. Okay, now this triangle ABC, from triangle ABC we need OC, sorry, we need AB, because AC we know. Okay, so we need AB. So triangle ABC, you see cos 60, if you consider cos 60, so this is the adjacent or base of the triangle. If this is the acute angle 60, this is the adjacent or base, and this is the hypotenuse. So cos 60 is equal to this AB by AC. So AC you know, so AB is equal to AC cos 60. So AC is equal to 6. Now cos 60 you know half, so it is 3 meter. So this AC, so AB is actually 3 meter. We got 3 meter. Now what we can consider, because if this AB is 3 meter, what could be then this H? Because this total height of AO should be equal to AC. AO should be equal to AC, that is 6 meter. And we need H. H is BO. BO is H, which is nothing but AO minus AB. AO is 6 meter. AB we got 3 meters, so it is again 3 meter. So height is 3 meter. Therefore, the potential energy gained by the girl is M into G into 3. H is 3. So 40 into 9.8 into 3. So 1176 joule. This is the answer. Let's see how many of you have answered it. I got answer from Rupam, Shurjani, Bunny. All of you have answered it. What about Oishi, Ognivo? Oishi and Ognivo? You got this answer? 1176? Okay. Now, here's another type of question. Little bit different. But this type of question actually, most of the time we can see in various papers. Okay. Let us try it. So a hemisphere, again a hemisphere is there. A hemisphere is there. Hemisphere, okay. Now this is a frictionless hemisphere. Frictionless hemisphere of, so if this is the center of this hemisphere, the radius is given, it is R, capital R, and this is a frictionless hemisphere. Okay. Now what is the statement? A ball of mass small m is pushed down the wall from A. This is A point and this is B point. From point A point A. It just rises up, to the edge, to the edge of the hemisphere, to the opposite edge of the hemisphere. So that means if it falls from A, so it will rise up to the B, rise up to the opposite edge of the hemisphere, hemispherical ball. It is a ball type of thing. Okay. Okay. Calculate the speed with which the ball pushed down along the wall. Calculate the speed with which the ball is pushed down along the wall. So in this diagram it is also given the height from A to the ground, that is this thing is H. Also from B also it is H. So how to calculate it? There will be no numerical value because you can see all of these are given in the parameters. They have given the parameters like R and H like that, so we'll be getting the answer in terms of them only. Acha, here maybe you got the question itself little bit having a problem with it. You just see this thing, just a simple thing. Here A is not the same height with B. So height of A, that H, so B is actually not the same height with. So here suppose this is the final height, which is actually same height as B, but A is little bit down, but the height of A is given H. This is H. Okay, so the position of ball you can see this is not exactly the top position. So that position you just consider to be H, and that is the position A. But the B is that exactly opposite side top position. That's all. That's all. You just modify it, and then you get me the answer of it. And the radius is actually given R. Radius is given R. Radius of this hemispherical ball is given R. Now get me the answer. What it will be? Simply you can do it. See, simple concept. We know energy, total energy is getting conserved. So energy at point A should be energy at point B. Now energy at point A, square root of 2g here. No, little bit changed. Just seeing. Uh, See, this is point A. Point A is actually h height from the ground, isn't it? So at point A, the total energy is, because point A is the not the maximum height. So here what is the maximum thing, that is R. This is the R. Okay, that is the R. Now point A is not the maximum. So at point A, what is the kinetic energy? Because it has been pushed with some velocity, correct? So I can consider it to be this thing half mv square, because it is pushed with some velocity. Okay, okay, pushed with some velocity from this edge. So at point A it is at h height, so it should gain some velocity, and then this position, due to the position, it should have this thing also, potential energy, mgh. So total energy in this case half mv square plus mgh for point A. This is the total energy, and that should be the total energy in case of, and that should be the total energy in case of point B. But the thing is that point B is the extreme of this hemisphere. So point B, at point B, you only have potential energy, no kinetic energy, because it is the maximum position over there. So at point B, you have only potential energy, and that should be your m into g into r, because here maximum height is r from the ground, radius of the ball, but the potential kinetic energy is 0, is the maximum position that it can gain. You should have the max of total energy getting converted to the potential energy. So half mv square plus mgh, that is the total energy at point A, is equal to this mgr, that is point B plus 0. Correct? Because total energy at point A is equal to total energy at point B. Now, so remember, that's what I have modified. Point A and point B is not in the same height. Point A is in height h, and point B is actually the maximum, that is r, the radius of the ball. So from here you need to get the speed v square. So half mv square is equal to mgr minus mgh. Therefore mm you just cancel it. So, and then v square is equal to 2 times of g, take common, r minus h. So therefore v is equal to square root of 2g r minus h. So no Rupam, v is not 0, root over 2g into r minus h. Yes, that is the answer in this case. Okay, okay, yes. So that's all for today's class. Okay, uh, I'll take a class on Sunday morning if you are available. Definitely the class will be there. According to your availability, you can join. I'll share the link. That will be not with that will be some different topic, like that, you know, solid particle, that thing, like elasticity, surface tension, that type of things. Okay, so Sunday 11 a.m. if you are available, whoever else will be available, they can join. Classes will be there. Okay, so we'll be joining. Okay, 11 a.m. Sunday. I'll share the link that time. Okay, that is that elasticity, that part, solid, mechanics of solid. Okay. No, vectors will not be explained on that day. I can explain one or two that relative velocity problem. Vectors are done actually. If you need relative velocity, I can explain one or two important problem for from relative velocity. You are asking for relative velocity, right? Because vectors are done. Okay, I'll explain some relative velocity problem. Okay, 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 okay. So I am ending here.